In the early 20th century, our understanding of the atom was about to change forever. Scientists like J.J. Thomson envisioned the atom as a plum pudding, a sphere of positive charge embedded with tiny negative electrons. But then came Ernest Rutherford and his groundbreaking gold foil experiment, turning the atomic world upside down. Rutherford's experiment, conducted in 1909 by his students Hans Geiger and Ernest Marsden, aimed to probe the structure of the atom using newly discovered alpha particles. Little did they know they were on the verge of a momentous discovery that would reshape our fundamental understanding of matter. Imagine a thin sheet of gold foil, only a few atoms thick. This delicate target was bombarded with a beam of alpha particles, positively charged particles much smaller than an atom. The expectation, based on the plum pudding model, was simple. Most alpha particles would pass straight through the foil with minimal deflection. After all, the positive charge of the atom was thought to be spread out evenly, not concentrated enough to significantly alter the path of the particles. To detect the scattered alpha particles, a zinc sulfide screen was placed around the gold foil. When an alpha particle hit the screen, it produced a tiny flash of light, allowing Geiger and Marsden to meticulously record the scattering pattern. As the experiment commenced, something extraordinary happened. While most alpha particles did pass through the foil with slight deviations as expected, a small fraction were deflected at very large angles. Some even bounced directly back towards the source. Rutherford later described this as almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Clearly, the plum pudding model couldn't account for such dramatic scattering. These unexpected results led Rutherford to a revolutionary conclusion. The atom must contain a tiny, dense and positively charged nucleus at its center. This nucleus, he reasoned, was responsible for the strong electric field that could significantly deflect the path of positively charged alpha particles. The vast majority of the atom's volume, he concluded, must be empty space, populated only by the tiny, negatively charged electrons orbiting the nucleus. Rutherford's nuclear model of the atom, born from the gold foil experiment, became a cornerstone of modern physics. It paved the way for a deeper understanding of the atom, its constituents and their interactions. The discovery of the nucleus marked the birth of nuclear physics, a field that would go on to unlock the secrets of radioactivity, nuclear energy, and the very nature of stars.